Hey guys, let's suppose that you have a function f of x is equal to x cubed plus 1 over that quadratic. And let's suppose that you're being asked to identify any horizontal and slant asymptotes if they exist. What you have to do is, well, just look at the degrees of the numerator and the denominator. It turns out that the degree of the numerator is equal to 3. The degree of the denominator, q, is equal to 2. So that means that the difference between P and Q, or the degrees of P and Q, is 1. So that means that we're going to have a slant asymptote. And in order to determine the slant asymptote, we have to do long division such that we are dividing x squared minus 2x plus 3 into x cubed plus 1. Okay. So I'm going to go to the next page and actually perform the long division. So we have x squared minus 2x plus 3 divided by, well, it's not divided by. Let's do a new page. Didn't give myself enough room. Minus 2x plus 3. And then we have x cubed plus 0x squared plus 0x plus 1. Remember, when we're doing long division, we can't skip any of the terms. We just have to use zeros as placeholders, and it's helpful when we're actually doing the long division. So x squared goes into x cubed one time, or x times. So that gives us x times x squared is x cubed. X times negative 2x is negative 2x squared. X times 3 is 3x. And just like regular long division, we're subtracting each line. So the x cubes cancel. We get positive 2x squared, and we get a negative 3x, and then we bring down the 1. And now we're going to continue again. X squared goes into 2x squared 2 times. So this is plus 2. So 2 times 2 times x squared is 2x squared. 2 times negative 2x is negative 4x. And then 2 times 3 is 6. So now we're subtracting each line. This cancels, and then we're left with positive x and minus 5. So our quotient is x plus 2, and our remainder is x minus 5. But when we're looking for the slant asymptote, all we're looking for is the quotient. The quotient tells us what our slant asymptote is. So that means our slant asymptote is going to be y equals x plus 2. It's linear. And there are no horizontal asymptotes. So let's just look at the graph of this so that we can gain some intuition for what we mean by slant asymptote. So our graph was, we'll just call it g of x, but we have x cubed plus 1 divided by x squared minus 2x plus 3. Okay, and I'm also going to plot our slant asymptote. Our slant asymptote we established was x plus 2. So let's look at our graph of our curve, g of x. As x approaches infinity, as x gets larger and larger and larger, our y values are trending towards the slant asymptote x plus 2. It's almost as if g of x becomes x plus 2. It's almost as if g of x becomes y equals x plus 2 as x gets bigger and bigger and bigger. And the same can be said as x approaches negative infinity, as x gets closer and closer and closer to negative infinity, which it can never actually become. G of x is actually becoming, it's almost becoming y equals x plus 2. So this is a good example of a graph where our function is approaching our slant asymptote. And also look here. Our function actually crosses the slant asymptote. So the function can be defined on the slant asymptote. That's something to note.